Okay. So, good afternoon, all. Yes. Okay. So, today we are going to discuss ORD spectra. So, you know that ORD nothing but with the optical rotatory dispersion. Means like this is different spectroscopy like the previous spectras like C13, okay, H1 NMR and mass spectras. So here the ORD spectra, generally it is used to assign the configuration and the conformation to the compounds. Okay, so you know that configuration confirmation, like confirmation, okay, so EZ confirmation, right? So configuration, RS configuration. So with help of this ORD spectra, so you can assign the configuration to this particular compounds. And in this, some terminologies involved in this ORD spectra. And see, okay. So ORD curves and Octane rule, right? So Barton effect, circular dichroism. So all these are the some important terminologies which involves in the ORD. Okay, so basically the principle, if you see the principle of this ORD spectra, right? So generally the light, okay, the light which is it is not a unidirectional, so it is multi-directional here. So the light which is having various directions, there is no particular direction in this particular light here. And when that light is passed on the object, right? So it will be passed through various directions here. So here when that particular light is focused on the monochromata, we call the right. So prism monochromata here. So it will be okay scattered through that particular prism and will be passed through that prism and it pass in a one direction. Okay. So we call that is a plane polarized light. Okay. So when this plane polarized light passes through this particular prism or the what is that called it's different arrangements. Okay. So it will be passes or it travels in a one direction here, right? And that direction it will, okay, so we call that is a, right, plane polarized light. Here you can see in this particular diagram, right? So this is the normal, the ordinary light here, right? So this is your ordinary light, and when this ordinary light is passing on this prism here, right? So this is the prism. So when it is passing on this prism, right, or any some other arrangements like prism kind of equipments is there. So when it is passing on this one, so this multi-directional light will be converts into unidirectional, right? One direction. Here you see X, Y, Z, something, all the directions. You cannot, it is not having a particular direction here, orientation, right? So when it is passing through this one, so it is having only one direction. This is the unidirectional light, right? Unidirection, unidirectional light, right? And this unidirectional light is called the PPL. Okay, this is called the PPL. This is your ordinary light. This is ordinary light. This is plane polarized light here. This is the difference. Ordinary light will have the multiple directions, and PPL, plane polarized light, have the only one direction here. Okay. So this PPL light, when it is passing through the polarimeter, right? When it is passing through the polarimeter, so that light will be, okay. So it polarimeter, which is contain the compound, okay, which is contained in the compound. When the polarimeter is filled with the a particular compound, and when we pass the PPL, plane polarized light, so that light will be either it is rotated towards the left side or the right side. Two possibilities, right? So the light will be rotates towards the left side, or it will be rotates towards the right side. Okay, so based on that orientation, based on that rotation of that light, so we'll assign the configuration to particular compound here, right? And the very important and fundamental condition for this is the compound must be chiral. Okay, so only chiral compound will rotate the plane polarized light here, right? Only chiral compound will rotate the plane polarized light. The achiral compound don't rotate the plane polarized light, right? So the chiral compound means when that medium is chiral here, okay, chiral medium, so it will be rotates towards either towards the left side or the right side. Here you can see, yes, you see circularly polarized light here, right? So here is some light you see. This is the plane polarized light here, okay, and this is symmetric one, right? So this medium is a symmetric medium. Okay, this medium is a symmetric medium here. So it rotates the light. Okay, this is the light here, right? So with equal proportion, it rotates the light with equal proportion. Here E R, okay, light E nothing but it is energy generally, and E R, and on left side EL, left. R stands for right, L stands for left here. E stands for the light, means the energy general. It is energy, right? Because the light is okay, the form of energy only, right? Mm. So because this medium is a symmetrical medium here. This is the symmetrical medium, means achiral. Okay, the medium is a symmetrical, nothing but it is a achiral medium here. So you see the light is traveled left side and right side with equal proportion, right? So the net polarization, right? The net rotation is zero because you see here EL, okay, here EL equal to ER equal to EL, right? So that rotation is zero, right? So the theta nothing but the rotation, angle of rotation here. So it is zero. Net to rotation is a zero here. So there is no means there is no result in that particular rotation here. zero means rotation here. Okay. So why you are getting zero is rotation means the compound is not a chiral compound. It is a chiral compound. That is a chiral symmetric medium here. Okay. Now we'll see another example with the chiral compound here, means asymmetric compound. Here you see this, the medium is a asymmetric medium. Okay, the medium is a asymmetric medium. Same, we are passing that PPL here, right? So we are passing the PPL here. The X is the PPL here. So we are passing PPL through this asymmetric medium. This is the asymmetric medium here. The previous one is the symmetric medium. Now what is happening? You see this particular, right? So compound, because it is having the chiral compound, right? So this compound rotating this PPL. This is your PPL here, right? This is PPL. So it is rotating this PPL towards here the right side. Okay. So the configuration is positive, right? The configuration is positive here. Means what is that? Dextro rotator. Dextro. Okay. So it is dextro. Okay. So like that. If it rotates towards left side here, okay. So then it is lever. L. Okay. Lever here. So like that. Yes. Now the circular birefringence. So circular birefringence is nothing but where the rotation of the plane polarized light towards left side and the right side. Okay. So that means the ability. Okay, the ability to rotate the plane polarized light either left side or the right side. Right. So that phenomena is called the circular birefringence. This is one of the important definition here, right? The ability of the compound to means the ability of the compound. So which kind of compound able to rotate the PPL here? Only asymmetric medium or the chiral compound here. Asymmetric compound or the chiral compound. They're able to rotate the PPL either towards right side or the left side here. Okay. So and that phenomena is called your circular birefringence here, and circular dichroism. Right? So circular dichroism generally when that right. So when two components of plane polarized lights are observed, right? So among these two, so one will have the more ability to rotate the plane polarized light. Another is having the less. Means here E. Okay, so ER. Okay, so E is not equal to EL, right? Or EL is not equal to ER. So this is called the CD. CD nothing but circular dichroism. Circular dichroism nothing but the unequal, right? The inequality in the rotation of the plane polarized light is called the circular dichroism. And Cotton effect. So it is the combination of the circular dichroism and your what is that? Circular birefringence, right? CB plus CD. Okay. CB plus CD equal to CE. Okay. CB is a circular birefringence. CD is a circular dichroism. Circular birefringence and circular dichroism is called the means combination of these two is called the Cotton effect. Okay. And Cotton effect is very important application to assign the configuration to the compound here. Means cyclohexanone derivatives, right? Here is a cyclohexanone. Okay. So to assign the configuration or the conformation of the cyclohexanone, right? So we'll take the help of your Cotton effect. So as per Cotton effect, so assign that particular cyclohexanone derivatives configuration to the cyclohexane derivative. And what is a Quaternion effect and what is that? So we'll see later. First, we'll see that ORD curves here. The different curves are observed in the ORD spectroscopy. Here we have two types of curves. One is ORD curves and plane, right? So ORD curves means optical rotatory dispersion curves here. In this ORD curves, we, again further classified into two types. One is plane ORD curves and anomalous ORD curves. Yeah? So plane ORD curves where it is not having what is that? So crest and trough here, right? So you know that this is the crest and this the right. So in a means wave movement, you know that where the highest point is called the crest here, right? And the lower point is called the trough. Okay, so crest and trough. Right, so but so in the means in the wave nature of the light, okay, in the wave nature of the lights we observe these crest and trough here, but in the what is plane curve, okay, in the plane curve we won't observe the crest and trough here. It appears, right, so a simple line here which is means it is some lines will be about to this zero, right? So zero rotatory line here. We call this, what is it? Yeah, zero cross zero rotation axis here, right? So here we call this the zero rotation axis. Okay, right? So this is your zero rotation axis here, which is zero rotation axis, and some lines will be crossing, right? Here you see it is crossing the zero, right? So it is, you see here from top to bottom, and it is crossing your zero rotatory axis, and here also it is crossing zero rotatory axis. Okay, so from top to bottom, right? So from top to bottom, that you see this line, okay, this curve is passing from bottom to top by crossing the zero rotatory axis here. So it is because it is right. So it is locating towards, right. It is passing towards upwards here because to this zero rotatory axis, the above lobe means above coordinate or the above plane is called the positive phase. Phase is called the positive phase, and below one is called the negative phase here, right? So here this particular this line is the curve is, it is passing from below to above. Okay, means what is called, it is bottom to top here. So it is positive, it is passing, it is traveling towards positive what is that the above lobe here, above phase, above phase. Okay, so it is we assign with the positive sign, and here you see it is down, it is traveling towards downwards here, downwards, so it is negative sign, negative signal or the negative sign is assigned to this, right? So these are the plane curves, means we don't have any crest and trough kind of uh, right, so nature here. And abnormal ORD curves, so in the abnormal ORD curves generally we will observe the crest and trough here, right? We can observe the crest and trough, and here also where that particular, right, so curves which is having the crest, right? So crest point we assign with the positive, right? So positive sign here, and which are having the trough. Okay, trough, it is indicated with the negative sign here. So here the types of curves also important. Plane curves and right, the ORD curves. Sometimes they will ask discuss the ORD curves here or explain about the ORD curves. So ORD curves are two types: plane curves and what is that? Plane curves and what is one more here? Yeah, abnormal curves. And sorry, anomalous curve, not anomalous curves and anomalous ORD curves and plane curves. Next, so octane rule. This is very, very important for the long question. Right? 12 marks. Right? Octane rule is very, very frequently asking other. Repeated every time it is repeating. Right? Every time it is repeating that octane rule. Yes. Let's see what is octane rule here. So, yeah. So this octane rule is one of the important okay, so important application to assign the configuration to your cyclohexanone. Okay, so generally the octane rule, it is combination of circular dichroism and circular birefringence. CD plus CB equal to CE. Okay, yes. And this particular octane rule, it is right. So it is proposed by various scientists. You see, like Moffat and Woodward, right? So Clean and Hijazi, 1961. So all these are scientists who work on this. They who right, propose this octane rule. As per rule, this octane rule. Okay, so you have the some points you can see. The rule permits a prediction of the sign to the cotton effect for optically active cyclohexanone from their structure, configuration, and conformation. Okay. And here you see the carbonyl group should occupy the head of the chain or the board conformation. The system is viewed along with the CO, means carbonyl bond here. And the cyclohexanone system is oriented in a three-dimensional coordinate system with its original situated midway between the CO bond. Right here is the picture diagram. You can see that the bisect of your cyclohexanone, and you see here to this cyclohexanone there are three. Okay, so there are three planes, right? So yeah, the three planes are passing through this cyclohexanone. Okay, so here that there are three planes here, plane A, and this is plane B, and this is plane C. There are three planes are passing through this cyclohexanone here. Okay, so one plane A, right? So plane A is passing through what is this? Yeah, it is numbered here, right? Given numbering here. Sorry, yes, yeah. Yes, so with the number 1, 2, 3, 4, 5, 6, right? So here your plane A is passing through the uh, 4. Okay, here is a 4, and yeah, yes. Plane A passes through the carbonyl oxygen here. Okay, and C1 and C4. Okay, C1 and C4. C4 both axial and equatorial bonds. Okay, and plane B. Okay, so plane B is passing through the carbonyl oxygen C1, C2, and C6. Here you see, right? So plane B. Okay, here this is your plane B here. So C2. Okay, and here the carbonyl oxygen C1, right? And below, yes, that much one. And your plane C is okay. Your plane C is exclusively passing through your carbonyl group only, right? Only carbonyl group, right? So yes, here the plane C, it is bisecting the carbonyl group. It is passing through that carbonyl bond here. Based on this, these three planes, so we divided this. Okay, we divided this cyclohexanol, right, into two sectors here, right? Two sectors, and the two sectors are further divided into 8 sectorials or 8 coordinates. Two sectors further divided into 8 coordinates here. And in the 8 coordinates, the 4 coordinates are nearer to the observer and means front coordinates, and the another 4 coordinates are the rear side coordinates or back side. Rear means far away. Okay. So and front are the near coordinates and far rear side coordinates. And generally the rear side coordinates are the mirror images to your front coordinates here. So we'll consider any one, okay, because we consider only 4 coordinates, not 8 coordinates here. But generally it is having the 8 coordinates. But the first 4 coordinates here you can see, right? So here it is divided into right. So 4 coordinates here, 8 coordinates, but these 4 here you see, this is the okay. This is your upper left. Okay. This is upper right, UL, UR, and lower left, LL, and upper right, UR. Okay. Upper left, lower left, upper right, sorry. Yes. Lower. This is this is upper left. Okay, also. This is upper left, UL, and lower left, LL. Right? LL. This is LL. This is upper left here, and this is lower left, LL. And here is a so here the 8 coordinates and among these 8 coordinates, so okay, so because based on these 3 planes, right? Based on these 3 planes, we are divided into 8 coordinates. Sorry, 2 sectors, and with help of these 2 sectors, it is further divided to 8 coordinates, and in the 8 coordinates, 4 are okay. 4 are mirror images to the another. So we consider only 4 here. Among these 4, we have these types. You see, here is a upper left here, and this is lower left, and here is a upper right, and here is a lower right, LR. Here is some mistake is there. So this is not upper, it is lower left, right. Okay, so these are 4 coordinates. Okay, and you see here, this is the positive sign. Here is a positive sign here. This is negative sign. This is your negative sign, right? So upper left is a positive sign, and upper right is a negative sign here, and lower left is a negative sign, and lower right is a positive sign. Okay, so now you will see, just you okay, so you take the chair conformation of your cyclohexanol, and you see in which coordinate that groups are falling in. So based on that, we can assign the configuration. Okay, for example, you see, yeah, in the application part, we'll see. Right, so here in the Right, so in this trans 10 methyl to dichrone, sorry, decalone, right? So trans 10 methyl to decalone. You see here it is exhibiting the positive sign of the octane, right? So octane effect. So you see, you assign based on that octane, sorry, cotton effect. So you can assign the configuration here, right? So you can apply the octane rule to this particular cyclohexanone derivative, right? So in the decalone, methyl decalone, right? So you see here the at C9, right, and C10 and C1 and C8 here. So if the means the observer will be see the molecule from this direction, right? So when you are observe this molecule from this direction, right? So this particular methyl, okay. So this particular methyl is okay. So it is falls in the which side here? So it is observed in the yeah. So it is observed in the left side actually, right? It is observed in the left side. But here the hydrogen, right? The hydrogen, the least priority group should not be about, right? It should not be towards the observer, right? So as per CIP rules, you know that CIP rule, right? Kohn-Ingold-Prelog rules. So as per CIP rule, the least priority group must be away to the observer. Okay. So when this observer is viewing the molecule from this carbonyl group here, okay. So the methyl group is falls in the left side actually, right? And this hydrogen is falls in the right side. Means it is nearer to this observer. So as per this, we are getting the S configuration. Okay, but generally, if the least priority group is nearer to the observer, the above the plane, so you have to take the reverse configuration. So it is the R configuration. Right? So I have some work, so I'm stopping here. So we'll see you in the next. Thank you.